Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good day. We are now in chapter 2 for subject BHA1113 Engineering Materials. So for today, things that you are going to learn is, as for the chapter objectives, is said, number 1, all students should be able to explain and discuss the atomic structure and bonding. Number 2, students should be understand the relationship between crystal structure of metals and its atom arrangement. And number 3, students should be able to identify and differentiate the imperfection and defects in crystal structure. As for the lesson objective, at the end of the semester, students should be able to analyze and illustrate the materials atomic bonding as well as crystal structure. So for today, we are going to look at on these topics. Number 1, atomic structure and bonding. Number 2, we're going to look at on crystal structure of metals, which includes BCC, FCC, and HCP atom arrangement. Number 3, imperfection as well as defects in crystal structure. So for the first topic, which is atomic structure and bonding, we are going to learn on what is atomic structure. Well, in atom, you can find there are 2 items exist in atom, which are nucleus plus electrons. So if you refer to this figure here, you may find there's a nucleus here, and there are electrons with protons and neutrons in it. And in atoms, there's valence electron exists in it, which are the electrons that occupy the outermost field shell. These electrons are extremely important as they participate in the bonding between atoms to atomic and molecular aggregates. And most the electrical, mechanical, chemical, and thermal properties of the atoms of solids are based on this valence electron. For example, if you take carbon with the atomic number of 6, there are 3 shell for carbon exist, and the valence electron represent for the outermost field shell there with the value of 2. And there are other elements with various value of a valence electron, as can be seen in this table, starting from hydrogen, helium, lithium, and so on and so forth. So the value of valence electron can be varies as well, like either 1, 2, and 1, 2, 6, and so on and so forth. Yeah. If we refer to this periodic table, to the left, it means that the materials are ready to give up electrons to become positive ions. So it is known as electropositive elements. Meanwhile, to the right represent the electronegative elements, whereby the materials are ready to acquire or to receive electrons to become negative ion. And another things in atomic structure and bonding, things that you need to know is on the electronegativity. Electronegativity is the tendency for an atom of a given chemical element to attract shared electrons when forming a chemical bond. An atom's electronegativity is affected by both its atomic number and the distance at which its valence electrons reside from the charged nucleus. The value for electronegativity ranges from 0.9 to 4.1. And if you refer to this periodic table, to the left represent smaller electronegativity, and moving to the right represent larger electronegativity. So basically, the larger the values of electronegativity, meaning the material have more tendency to acquire or to receive electrons. In atomic structure, there are two major types of bonding, which are primary and secondary. In secondary, can be divided into three, which are ionic bonding, metallic bonding, and covalent bonding. While for ionic bonding, it is a type of chemical bonding that involves the electrostatic attraction between oppositely charged ions or between two atoms with sharply different electronegativities and is the primary interaction occurring in ionic compound. If you refer to the example, natrium chloride over here, you can see natrium have a positive value and chloride with negative value, and they will attract with each other, producing natrium chloride. So this is ionic bonding. If we refer to the periodic table over here, moving to the left, again, the elements over here is ready to give up electrons to become a positive ions, and moving to the right, it means that the materials are ready to acquire electrons to become negative ion. Ionic bonding actually hard because particles cannot easily slide past one another. There are good insulators because there are no free electrons or ions. Number 3, ionic bonding are brittle and tend to cleave rather than deform because bonds are strong. And number 4, it have high melting point because ion bond are relatively strong. And number 5, ionic bonding, some in ionic bonding, some are transparent because their electrons are not moving from atom to atom and less likely to interact with light photons. Number 2 is covalent bonding. A covalent bonding is a chemical bond that involves the sharing of electron pairs between atoms. These electron pairs are known as shared pairs or bonding pairs, and the stable balance of attractive and repulsive forces between atoms when they share electron is known. So this is known as covalent bonding. If you, for example, CH4 over here, so the element of carbon over here sharing four element of hydrogen. Number 3 is metallic bonding. Metallic bonding is a type of chemical bonding that arises from electrostatic attractive force between conductive electrons and positively charged ions, metal ions. It may be described as the sharing of free electrons among a structure of positively charged ions. The valence electrons belong to the metal as a whole, or forming a sea of electrons for metallic ions. So it doesn't belong to any one atom, but they are part of the whole metal crystal structure, as can be seen in this figure. Metallic bonding, the properties of metallic materials are good ductility, good electrical conductivity, lustrous, and malleable. This figure showing again a illustration of metallic bonding, where you can find the positive ion there and valence electrons in the form of electron charge clouds over here. So it doesn't belong to any one atom there. Another types of bonding is a secondary bonding. So the one that we've learned just now is the primary bonding, and this one the secondary bonding. Secondary bond are not bonds with a valence electron being shared or donated. They are usually formed when an even charge distribution occurs, creating what is known as a dipole. Dipole represent the total charge is 0, but there is slightly more positive or negative charge on one end of the atom than on the other. For example, hydrogen over here. So this part is actually is coming from primary bonding, then from primary they attract with each other, forming a secondary bonding. And the other example then this one is like hydrochloric liquid as well as in polymer. As a summary for this part is that we can say for ceramic, there are ionic and covalent bonding exists in it with large bond energy. Whereas for metals, normally metallic bonding occur in it with variable bond energy because it depends on types of materials in it. And same goes to polymer. It have a covalent and secondary Okay, and so now let's move on to chapter 2, which is crystal structure of metals. In crystal structure, there are normally two types of crystal structure that we need to know, which is number one, crystalline materials and non-crystalline materials, or also known as amorphous. In crystalline materials, the atoms are normally packed in periodic or 3D arrays, whereby in amorphous, atoms have no periodic packing. And example for crystalline materials include metals, ceramics, and polymers. Whereas for amorphous, normally it occurs due to rapid cooling, and the structure is much more complex than crystalline materials. So this is the example for for crystalline materials, for example, quartz crystal. It can exist either in a single crystal or polycrystal. If we refer to this graph over here, volume versus temperature, below melting point it is in solid condition, or in crystal. It either can be in single crystal or polycrystal, but once it is being exposed to temperature, it will straight away melting and form a liquid. So for solid, it is very simple. From solid, it will change straight away to liquid when it is being exposed to heat. Meanwhile, for amorphous or non-crystalline material, below melting point, obviously, it is in solid condition, but when heat being exposed to it, it will start to soften before it changes to 100% liquid. The most common example that we can find over here is wax. So if you notice for the wax, when we expose it to heat, we introduce it to heat, then it will start to soften before it changes to liquid. And this one is the arrangement of the atoms, whereby also called as crystal structure. This one is called as the unit cell. In crystal structure, you may find terms which is known as space lattice, and inside space lattice is a unit cell. And there are parameters in lattice space that we need to know, like 3H length, A, B, and C, and 3 interaction angles with the symbols of alpha, gamma, and beta. Other than that, we may also come across with the terms of Bravais lattice in crystal system. So Bravais lattice refers to the 14 different 3D configurations into which atoms can be arranged in crystals. The smallest group of symmetrical aligned atoms which can be repeated in an array to make up the entire crystal is called a unit cell. There are several ways to describe a lattice actually. The most common description is known as the Bravais lattice. In words, Bravais lattice is an arrange of discrete points with an arrangement and orientation that look exactly the same from any of the discrete points. That is the lattice points are distinguishable from one another. Thus, a Bravais lattice can be referred to one of the 14 types of unit cell that a crystal structure can be made up of. Like this one, these are the 7 different types of a unit cell in Bravais lattice. Out of 14 types of Bravais lattice, some 7 types of Bravais lattice in 3D space are also listed over here, and the other 4 are the basic types of unit cell. This is the illustration for those crystal system just now, and same goes to this one. Basically, you may find all these 14 Bravais conventional unit in textbook that have been proposed to you before. Okay, now in crystal structure, we always we always wonder why some metals are hard and the other soft, and why some metals can withstand high temperatures while some others are not. Well, it actually depends on the structure, or to be specific, the arrangement of the atoms itself. For example, if the material have a packed and dense with atoms, obviously it will be much more harder than those materials will have much lesser bonding with a lower percentage of atomic numbers in it. So all those properties will influence the behavior of the structure. As mentioned to you just now, these are the metallic crystal structures that we are going to learn. Number 1 is BCC, FCC, and also HCP. Now let's look at one by one. For this one is for BCC, showing you a unit cell inside 1 mm. So this one you can just see the calculation. Okay, first of all, let's look at the simple cubic structure. Actually, for simple cubic structure, this one is very rare because it's because of its low density. So normally we don't use a simple cubic structure. The most common one is like BCC, FCC, and HCP. However, the way we calculate the number of atoms per unit cell is more or less the same. And the formula is N equals to Ni plus Nf over 2 plus Nc over 8. And this Ni represent the number of interior atoms, and F represent the number of its atoms, and C represent the number of corner atoms. Now let's look at how do we calculate APF, atomic packing factor. Before that, let's do this example to calculate the number of atoms for simple cubic structure. So N equals to, is there any interior atom for SC? No, so equals to 0. Atomic, the number of face atoms, so no face atom, so 0 over 2, plus number of corner atoms. Yes, there are 8 corner atoms exist in SC. 1, 2, 3, 4, 5, 6, 7, and 8 at the back. So 8 over 8 altogether equals to 1. Now let's calculate the APF just now. This is the formula, which is equals to volume of atoms in unit cell divided by volume of unit cell. And for volume of unit cell, this one is very simple. Straight away A power of 3A cube, because this length A times A and times A. So A cube there for volume of unit cell. Meanwhile, for volume of unit atoms in unit cell, you need to times the volume for sphere for each atoms times with number of atoms in that crystal structure. So in this case, for spheres, volume for spheres equals to 4 over 3 pi r cube. And r over here is 0.5a. So just substitute into the formula, and don't forget to times with number of atoms in the cube. And finally, you should be able to get the value of APF for SC equals to 0.52. Now let's move on to number 2, which is BCC. Again, the same formula being applied in order to calculate the value of atoms number. N equals to, is there any internal atoms in it? Yes, there is 1. So 1 plus phase atoms. Is there any phase atom in BCC? No phase atom. So 0 divided by 2 plus, is there any corner atoms there? Yeah, there are 4. There are 8 of it. So 8 over 8. And altogether equals to 2 atoms per unit cell. Now we have to calculate the atomic packaging factor APF. However, in order to calculate the APF, we need to find the relation between A and radius there. Okay, this is the BCC crystal structure. If you notice the triangle over here, refer to that one, then start you need to find this hypotenuse, because this hypotenuse actually equals to 4r. Okay, so now next moving to a formula for APF. Same, this one for volume per unit cell, A power of 3. And then for the upper part, you need to times the volume for each atoms times with number of atoms in that crystal structure. So 4 over 3 pi r cube. R equals to this value. So times with number 2, and you should be able to get the value of APF equals to 0.68. Okay, so the number 3 is FCC. Again, you need to calculate its atomic number over here. And equals to, is there any internal atoms there? No, then 0. Plus, is there any phase atoms there? Yeah, there are 6. 1, 2, 3, 4, 5, and 6 at the bottom. Divide by 2 plus 8 because of the corners atoms there. Altogether equals to 4 atoms per unit cell. Then before you calculate the value of APF, you need to find the relation between 4R and cert 2A over here. Well, normally when question being given to you, the cert 2A is not there. Only 4R over here. So that's why you need to find the relation between 4R and cert 2A. Square root 2a. So square root 2a is obtained from this one, yeah, this triangle. So a square plus a square, square root both of it, then you should be able to get this hypotenuse with the value of square root 2a equals to 4r. All right. So now you get this relation and you also have calculated the value of atomic numbers. And finally, you can calculate the value of APF. Yeah, again, don't forget to times the value of atomic number in that cell. So substitute all the information or the data there, you should be able to get the value of APF equals to 0.74. Okay. The last crystal structure is HCP. This one is slightly different than how do we calculate the value of number of atoms in it because of its complex crystal structure. Okay, now let's look at how do we calculate this one. Number one, for the internal atoms in it, yes, we do have 3. 1, 2, 3. So 3 plus for the surface, yeah, we do have 2 atoms at the surface, half atoms at surface, which is at the upper part and also lower part. So 2 times half plus at the corner atom there are 12 of it. However, this one actually hexagonal, so each corner at the atoms actually sharing 6 the atoms actually sharing six corners there. That's why 12 times with 1/6. So altogether equals to 6 atoms per unit cell. All right. Okay, so now for example, for this case, okay, this question given to you is that calculate the volume of zinc crystal structure unit cell by using following data. Pure zinc has the HCP crystal structure with lattice constant A. This one is A equals to 0.2665 nm, and C, the length, equals to 0.4947 nanometer. And C over A ratio is given by 1.633. So how do we solve this problem? The first one is that we need to find the area for triangle ABC. Formula for triangle, area for triangle is that 1/2 times width and times height, right? So you should be able to get this area for ABC. After that, since this is hexagonal crystal structure, then you need 2 times width 6, because it has 6 column over here. 1, 2, 3, 4, 5, 6. So altogether 6. After that, just to get the volume, its volume, then you just need to times with its thickness, which is C. So let's see the calculation. Again, area of triangle ABC, you should be able to get this data. Then times with 6, because total area for HCP base equals to 6. Then times with its thickness, because we want to find the value of volume. And finally, you should be able to get the value of 0.0913 nanometer cube there. So as comparison for those types of crystal structure, you may find that like a atomic packing factor is slightly different between one another. However, for FCC, HCP is more or less the same. And the examples of each crystal structures over there, I think this one you can read it on your own, because it is actually summarizing those from previous slides just now. Okay, now another part in crystal structure that you need to know is on how to calculate the theoretical density in crystal structure. This is the formula for density, mass of atoms in unit cell per total volume of unit cell. And over here represent number of atoms per unit cell. A represent the atomic weight. VC is the volume of unit cell. Na, the Avogadro's number. Well, Avogadro's numbers is fixed, so you can just reuse this value. Okay, let's see the example in BCC over here. By using the formula mentioned to you just now, So I think you can just straight away key in the information. And for the atomic number for this crystal structure, you already learn on how to find the relation between A and R. So from there you can just rearrange or interpolate it a little bit, so you should be able to get this value. And finally, by using the formula, you should be able to get the value of theoretical density, which is equals to 7.18 gram per centimeter cube. Meanwhile, for actual density equals to 7.19 gram per centimeter cube, or it can be 7.2 gram per centimeter cube. So in general, the density, we can see that the set density for metals is more higher than ceramic, and ceramic density is more higher than polymer. Why? Because the metals have close packing metallic bonding, and normally with large atomic masses. Meanwhile, for ceramic, it has less dense packing, normally have lighter elements, and for polymer have low packing density, for example, carbon, hydrogen, and oxygen, whereas for composite have intermediate values. And you may refer to this diagram or a graph over here to compare the density of different types of material classes over here. Now, crystal structure also have single, is either in crystal, it can be either single or polycrystal or polymorphism. For single crystal, properties vary with direction, is called as anisotropic. For example, like BCC, yeah. So this one, anisotropic. Meanwhile, for polycrystals, properties, it may or may not be vary with direction. If the grains are randomly oriented, is called as isotropic, and if the grains are textured, it is known as anisotropic. So this figure actually showing the difference between isotropic and anisotropic. Meanwhile, for polymorphism, it refers to the two or more distinct crystal structures for the same material. For example, titanium, it has alpha and beta titanium in it. Same goes to carbon. It has diamond and graphite in it, yeah. Okay, the last topic for today is the imperfection and defects in crystal structure. All right. So basically, the defects itself will affect the properties of the material. So we'll see how it will affecting the final properties of that material, because sometimes we do create that defects because we want to change its properties due to certain functions. And sometimes it may happen due to incidents, yeah. Well, it depends, and we have to investigate those phenomenon. All right. For types of defects, there are three types of defects that we need to know. Number one is point defects, like vacancy, atoms, interstitial, and substitutional. For line defects, dislocation, and area defects is grain boundaries. This is what does it mean by vacancies and interstitial. For vacancies, vacant atomic sites in a structure. So you can see there's a vacancy in that structure over here once the plane being distorted. Meanwhile, for interstitial, you may find there's an extra atoms position between atomic site once the plane being distorted. After that, in ceramic, The vacancies exist in ceramic for both cations and anions. Just now is the point defects in metals, because you can see the atomic sizes is the same. And for ceramic, it consists of anions and cations, so it can exist in either both of them. And same goes to interstitial, exists for cations. Interstitials are not normally observed for anions because anions are large relative to interstitial size. So you can look at you can refer to this figure here, the cation interstitial, cations vacancy, and anion vacancy. Now let's look at the example for imperfection in ceramic, like natrium chloride over here. If this one is the atom without impurity, and suddenly there's a CO2 plus impurity exists in natrium chloride, whereby calcium over here will attract natrium plus there, and finally it will happen cation vacancies in that crystal structure. Same goes to anion impurity. For example, this is without impurity, and suddenly oxygen impurity exists in the crystal structure, which will attract chloride towards it, and finally there will be anion vacancy exists in that crystal structure. Whenever there's an impurity in that crystal structure, it must maintain the charge balance. The charge balance still need to be maintained. That's why for both cases, for this one, calcium will attract natrium, and oxygen, it will attract chlorides towards it. Another types of defects, which is point defects. This one happens due to part in change packing errors and impurities, such as chain ends and side chain. And this one is the line defects. It occurs between crystal planes, results when dislocation moved, and this one will produce a permanent deformation or plastic deformation. So if you refer to this figure or illustration over here, once the plane is lit, then it moves until to the end, and finally creating a permanent deformation over here. So same goes to this one. This is the specimen that you might find. This is the original one before dislocation, this one after dislocation, and it will stay that way even though the forces acting on it being removed. And types of dislocation that we can find is that either edge dislocation, screw, or mix both of it, and it exists during solidification or plastic deformation, or as a consequence of thermal stresses resulting from rapid cooling. This is the illustration of what does it mean by edge dislocation. This one is edge dislocation, figure A, and figure B is screw dislocation. I think the next figure showing you much more detailed illustration. This one is edge dislocation. If you see, the direction of motion actually perpendicular towards one and another, whereby for a screw dislocation, you can see even though it's moving the other way around, however the direction of motion is like it is being twisted a little bit there. And again, this one is the illustration for edge dislocation. Sorry, just now okay, yeah, edge dislocation. So if you refer to this one, to its much more clearer view over here, once there is a distortion, then it will moves until it reach point where it will become a permanent defects over there. You see these types of imperfections or dislocation in any types of in that material can be easily noticed through optical microscope. So for example, this one, you can see the line, these such lines exist on that material. So this means that materials are having a edge defects or lines defects over there. Other than that, grain boundary defects may also happen at grain boundary. Okay, we can see that, for example, by referring to this figure over here, the orientation is changing. This is the grain boundary, and these are the arrangement of the atoms. It changed slightly over there. So this is called as the grain boundary defects. And you may see the angle of misalignment over there. Oops. Okay, so that will be the last parts in imperfection and defects in crystal structure. So as a summary, point, line, and area defects do exist in solids. And number two, the number and types of defects can be varied and controlled, either using temperature controls and so on and so forth. Number three, defects may be desirable or desirable. Well, it depends on types of product that we want to produce. Sometimes we do want to have that types of defects, and sometimes we don't want it. However, we still need to calculate all those defects so that we always come up with an optimum design for such products. With that, I thank you very much for your kind attention and time, and we'll see each other again in the next lecture, which is actually in chapter 3. So this will be the end of chapter 2. You should be able to expect for quiz in the next lecture. So with that, thank you very much, and thank you. Bye.